All right, lesson 1.5 is a review for us anyway of prime factorizations. And so when you are done with this unit, you should be able to do basically two things and then relate it to certain other ideas. But be able to identify prime and composite numbers. Those are a couple of vocabulary terms that we need to be able to understand. And then you need to be able to find the prime factorization of composite numbers. And so basically a prime factorization is when we break numbers down into its prime numbers. So first of all, a couple of terms you need to know. First of all, a prime number. So you'll want to get these down over to the side of your notes so that you can refer back to them. A prime number is a whole number greater than 1. Okay, so it can't be 1 itself. That has exactly two factors, itself and 1. Okay, and so here is an example of a prime number. 5 is a prime number because it only has factors that can evenly divide into it of 5 and 1. Those are the only two things, so 5 itself and 1. So that is an example of a prime number. And now, when we go up here, we're trying to determine whether 19 is a prime number or not. Well, if you go through and you think about what are the things that go into 19, okay, and you can do this in a number of ways. I know that 1 times 19 is 19. Okay, again, we're talking about whole numbers here. Well, if I go through the rest of the list, well, 2 doesn't go, 2 times nothing goes equally into 19 anyway. Yes, you can put 2 into 19, but not equally. Well, 3 doesn't, because 3 times 6 would be 18. 3 times 4 would be, 3 times 6 is 18. 3 times 7 is 21, so we would miss it there. 4 doesn't, 5 doesn't, 6 doesn't, 7 doesn't, 8 doesn't, 9 doesn't, and so as you go through that list, you'll find that 1 and 19 are the only things that go into it, so it is a prime number. Okay. But then we get to 20, and yes, I did this on purpose in this particular case, 20, and I bet you can guess that 20 is a composite number. Composite numbers are numbers also greater than 1 that have more than 2 whole number factors. So it can be divided evenly by other numbers other than 1 in itself. And so in this particular case, we have some examples of composite numbers, like 4 is composite because it divides by 1 and 4, but it also divides by 2. Or the number 6. 6 divides by 1 and 6, but it also divides evenly by 2 and 3. 8 divides by 1, 2, 4, and 8. 9 divides by 1, 3, and 9. So in that particular case, we have a composite number. And so if you go ahead and think about 20, well, what are the things? And if you want to list them, if you need to list them, we obviously know that 1 times 20, and you'll notice I'm multiplying, or I'm listing these as pairs. 1 times 20 would be 20. I know that 2 times 10 would be 20. So there's 2 more factors of 20. Well, 3 does not go into 20 evenly, but 4 does, because 4 times 5 is 20. 6 does not go into evenly, 7 does not, 8 does not, 9 does not, and then we get into 10, which we've already used. So in this particular case, 20 has 1, 2, 3, 4, 5, 6 different factors. So obviously it's composite. And again, in each of these cases, we are looking into numbers that divide evenly, so no decimal remainders or anything like that. We want even answers, so to speak. No non-remainder answers. So you're going to do a little bit of that. And then we're going to get into prime factorization. And prime factorization is when we have a number that is written as the product of its prime numbers. Okay, so in layman's terms, it's written entirely as prime numbers. And in this particular case, we are going to talk about 2 different methods of doing our prime factorizations. I personally, I am more of a factor tree kind of a guy. But that's just probably because that's the way I was taught when I was young, and so I got used to doing it. If you prefer the second method, which I'll show you here in a second, again, to me it does not make a difference how you do it. And so, and actually I'm going to show you that in some of these cases, and the reason I like factor trees is because you can actually do them in 2 or 3 different ways and still get the same answer, where when you're doing the other method, which again I'll get to in a few seconds here, you have to divide by prime numbers only. So, okay, 36. Let's go ahead and I'm going to do 36 in 2 different ways. All right, so 36, I'm going to take and I'm going to divide 36 by any 2 numbers, or I'm going to come up with 2 numbers that multiply together to give me 36. So in this case, I'm going to go 2 times 18. 2 times 18 is 36. And you notice my little tree as I move down, it sort of looks like an evergreen tree, a Christmas tree when we get all said and done. Okay. Now 2 is prime, so I won't break it down any further. But 18, I can go, let's say, 2 times 9. 2 is prime, but 9 is 3 times 3. And 3 and 3 are prime, so this is as far as I can go. So my primes in this case are all of these numbers at the ends, the very ends or very bottoms of my branches. And so when I have this here, I have 2 times 2 times 3 times 3. Well, one of the things I'm going to have you do is I'm going to have you combine the like numbers into their powers. So 2 squared, that would be 2 to the 2nd power. That's 2 2's multiplied together. And 3 times 3, well, that's 2 3's multiplied together. So that's 3 to the 2nd power. So my prime factorization in this particular case is 2 squared times 3 squared. Now, if you reverse this and went 3 squared times 2 squared, it would be the same. So order of multiplication does not make a difference. Now, here's why I like the factor tree method. And I'm going to do this again using a different starting point. Okay? Is, let's say I didn't know that 2 times 18 is 36. I could use 2 other numbers that I happen to know are 36, like 4 times 9. Okay, because I know that 4 times 9 is 36. Okay, and so it gives me a different starting point. So I have different options of where to begin. Well, 4 breaks down into 2 times 2. Okay, 4 is a composite number. And 9 is 3 times 3. And these are now all primes. And you'll notice here, so I've got my 2, my 2, my 3, and my 3. I've got the same 4 prime numbers as I had over here. So it gets me to exactly the same place. 2 squared times 3 squared. And this is part of why I like factor trees, because you have the option of doing them in different ways, just depending on what your knowledge of factors are. So, okay, 280. Now, 280 has many ways that I can do it, and in this case, I'm just going to pick a way and go with it. You may, if you tried, you may have some other possible answer or way of doing it. So, and I'm going to go wide here because 280 is a big number. I'm probably going to have numerous factors. So, 280. Well, I'm going to start by going 20. I know that numbers that end in 0 divide evenly by 10, and so I know that 280 is 28 times 10. Now, you could have very easily gone 140 times 2, but I chose 28 times 10. So, all right, 28, I know, is 4 times 7. Okay, and I'm actually going to go ahead and finish this branch out. 7 is prime, so I'm not going to go any further with that. But 4 is 2 times 2. And 2 and 2 are prime, so I'm not going to go any further with that. So I know that part of my answer are these 3 numbers here. Now I'm going to go back up here to 10. 10 I know is 2 times 5. Well, 2 and 5 are both prime, so I'm not going any further there. So here is my list of prime numbers. And so now, and if you needed to, you could, some people will want you. I don't need you to sit here and list all of them out and then put them, if you wanted to. I would be perfectly happy with you going, okay, I've got 3 2's, so that is 2 to the 3rd power. I've got 5, and that is 5 to the 1st power. You don't have to write the 1, but we know that there would be a 1 there. And 7 to the 1st power, with or without the 1. It's not required, but you can put it there if you're comfortable with it. So in this particular case, my prime factorization is 2 to the third times 5 times 7. Now, the other method that we have here is the step diagram. Okay. Now, here is first of all, the important thing about the step diagram and the drawback of the step diagram is I have to divide this number 252 by prime numbers. It may not always be easy to come up with a prime number. Things that divide by 2 is prime. So you can, if it's an even number, you can always divide by 2. But sometimes it may not always be obvious what the prime number is that divides it. So, okay, oops, and then I messed up. Let me erase that, and let me write this correctly, 252. That's supposed to be a 5. All right, so what I'm going to do, and you sort of do this as an upside down division box. All right, so 252 divides by, obviously it ends in 2, so I'm going to divide it by 2. And so that's what I'm going to do. I'm going to go 252 divided by 2. My solution will actually move down here. That's 126. Okay? And then I have to divide and try to figure out, well, what prime number goes into 126? Well, it's an even again. So I'm going to divide this now by 2. That leaves me with 63. Okay? Well, what prime number goes into 63? Well, in this particular case, I know that 63 divides by 3. So I'm going to divide 63 by 3, and that gives me a solution of 21. And you'll notice the step part of this as it's stepping back. 21 divides by 3 as well and leaves me 7. 7 is a prime number, so I'm not going to go any further here. So my prime factorization, here are all my prime factors down the left-hand side. So my prime factorization is 2 times 2, which is 2 squared, and 3 times 3, which is 3 squared, and then times 7. So here is my prime factorization for 252. Okay. And as much as I say I'm a factor tree kind of guy, if this works for you, go ahead and use it. You're not going to make me feel bad if you prefer using step diagram. Okay. 495. All right. So we're going to step diagram 495. 495, I know, divides by 5, knowing my shortcuts. Things that end in 5 and 0 divide by 5. So 495 divided by 5 leaves me 99. Okay, and in this case, I do have some choices here. I know 99 divides by 11, and 11 is a prime number. So 99 divided by 11 is 9, and that's where knowing some of those multiplication tables come into play. 9 is a composite number that is 3 times 3, or 9 divided by 3 is 3. And so here are my primes now. So I have 2 3's. So that is 3 to the second power times 5 times, and this would be 5 to the first. You could put the 1 if you wanted it. You don't have to. I mean, we know that there's 1 5 here, and times 11 to the first. But again, in powers, we don't have to put the 1 if it's only one of them. So, but you have to understand that is 5 to the first, and that is 11 to the first. So there's our prime factorization. So there we go. We're all set with our prime factorizations. Your job is to go ahead and do a little bit of practice working with prime factorizations. Good luck.